Hey everybody, this is going to be the Unit 4 and 5 study guide. Let's go ahead and get started with this first box. Unit 4 and 5 are all about the applications of derivatives. The previous study guide was just about how to take the derivative. And now this study guide is about how do you use the derivative. There's many different ways we can use the derivative. So this first box talks about position, velocity, and acceleration. This is one of the most basic applications of the first derivative and the second derivative. So the position is usually associated with the original function. If you see a free response problem that's talking about the motion of a particle, it's usually with respect to time. So for these functions, I'm going to use t instead of x. So position will be associated with the original, and the velocity is the rate of change of the position, which is the speed or the derivative, f prime of t. So you take the derivative of the position to get the velocity. And then to get the acceleration, you take the derivative again, so the second derivative, so f double prime of t. And in free response problems, they may not be denoted with an f. It may be written with different letters, like this might be p, v, and a as their letters, but you still have to know that a would be the second derivative of p, for example. So you might see some free response problems. I'll post examples just so you can kind of see that. So they might ask you for different things like this type of vocabulary. If you see these words pop up, you'll know exactly what to do based on the formulas that we write here. So for displacement, you're trying to see where did you start and how far away did you end up from where you started. And so the way we do that is we can find the difference between our ending position and the starting position. So usually in these types of problems, they'll give you an interval from A to B. The particle is moving from A to B. If you want to find your displacement between point A and point B, or time A and time B, you would just subtract f of B minus f of A. And I'm referring to the original position. You take your ending position at the end time and subtract it from where you started off. What position did you start from? And another way you can do this is you could also, if you're given just the derivative or just the velocity, then this is also the area underneath the velocity graph. So right here, notice how if you take the antiderivative of f prime, you end up with f. This is basically the first fundamental theorem of calculus, which we'll get into in a different study guide. But in a nutshell, taking the integral of the velocity gets you back to the position, and if you evaluate from your time bounds, that gives you your displacement, where you started, subtracted, where you ended up, subtracted from where you started. To find the distance traveled, that means the total distance, meaning like including the path. So even if you change direction, it's including you went somewhere and it's counting all of your steps. Whereas the displacement is just counting the distance between where you started and where you ended. Distance traveled is counting all of the particle's steps or all of the particle's path. So this is almost the same thing. We just include absolute value bars. So integral from A to B, and we take the absolute value of the velocity. Absolute value of the velocity, integrate that. And in other words, that could also be equal to the absolute value of f of B, the original position, minus f of A, just like that. So it looks very similar to distance traveled, it just has absolute value bars. And now the last one is average velocity. So average velocity is, if you think about physics, the way you find your average velocity is you take the total, your displacement, and you divide it by how much time you're traveling for. So that tells you an average velocity throughout that time period. So all it is your displacement divided by the time period, or the time that's elapsed. So this is going to be the same integral for displacement. So A to B, integrate f prime of t dt. So we integrate the velocity, but we want to find the average of that. in this time period. So we divide by the time that is elapsed. So you could put a 1 over b minus a in front. And this is also the formula for average value of a function. So if you want to find the average value of something, you integrate it, and then you divide by the bounds subtracted. So there's the first box with position, velocity, and acceleration. That's one application of differentiation. The next one, the most basic one that we've covered so many times in class, is finding the tangent line approximation. And so here's your point slope formula. If you leave your tangent line in this form, it's you're good. You don't need to solve for y or anything. But you do need your slope, x and y coordinates. Plug all that stuff in here, and there's your tangent line. The next one is function analysis. This is a very common application on the AP test of derivatives. And I did do another video on this, but I'll walk us through it again one more time. So I'll start with the bottom row, f double prime. And we're using all these functions, f, f prime, and f double prime, to interpret things about the other graphs. So let's say, for example, our second derivative is positive. Then that tells me two things. That tells me that the original function is concave up, and it also tells me that the antiderivative of this guy right here, so one level up, is increasing. Positive is associated with increasing on the function that's its antiderivative. So at the same time, I can also say that if f prime is positive, then I go one level up and that thing should be increasing as well. Okay, so in this first column right here, these two guys are associated with each other, and then these three guys here are associated with each other. They all go, like, these two go hand in hand exclusively, and then these three go hand in hand exclusively. So I'll talk about how we interpret this in the next few boxes. Okay, then we could have the same situation, but our f double prime is negative. So now that tells me f prime is decreasing, and the original is concave down. And at the same time, we can still have a positive first derivative, which means we have an increasing original function. So once again, these three guys all associate with each other, and these two guys associate with each other, but they're not mixed together. We can only connect these two, and we can only connect these three. Okay, the same way I can find the other combinations, so I'll just write those down over here very quickly. We have positive, increasing, and concave up, whereas over here we have negative and decreasing. And then the last column, everything is going to be minus, decreasing, concave down, and then minus, decreasing. So now in the next few boxes, I'm going to explain this chart right here and how you use it. So if you write this chart down on your test, it's not going to give you any credit or anything like that. This is just for your reference to help you write the correct things. So if you want to interpret things using that chart, you can say, for example, I know this is a lot of stuff that I've written down. You can take your time and write it down. Just listen right now. But for example, if a question is asking, when is f increasing, you can interpret it in one way. So if we look, when is f increasing, I see on the chart I have f increasing in two of these columns. And in both of those columns, f prime was positive. So notice the sentence right here. I wrote f is increasing at some point or interval. You'll have to write that in based on the problem. And then you have to put the because. This is your justification, because f prime is positive at that point. Similarly, f can be decreasing at some point or interval because f prime is negative. And so that's kind of using the first derivative, because both of our justifications had the first derivative. The second derivative test can tell us about concavity. So f is concave up at some point or interval because, and you can write one of two things. You can either write concave up because f double prime is positive. So notice concave up is associated with f double prime being positive. Concave up, f double prime being positive. Or instead of writing that, if you don't know anything about f double prime, you can write about f prime. If f prime is increasing, then that tells you that the original is also concave up. Remember, these three things all go hand in hand and associate with each other. So you can write either one of these two clauses right here as your justification. We can also talk about relative minimums and maximums, or relative extrema. You can have a relative extrema at some coordinate, and your justification would be because that is when f prime changes sign. So for example, let's think about if f prime changed from positive to negative, it changed sign. Then your graph was increasing, it changed, its slope changed sign, and now became decreasing. So that means you have a relative maximum at the top of that. And so your justification would be, since f prime changed sign, I have a relative extrema at the top of that. Or if it was a negative to a positive, you have a relative minimum. And then absolute minimum and maximum is very similar, except for absolute, you need to also evaluate your endpoints. Your endpoints of the interval. So I'll just make a note of that down here. Your endpoints will be from A to B, or some two values that are on your graph or on your table in the given problem. And then just real quick as review, critical numbers is when f prime of x is equal to 0 or undefined. That's when you might have a maximum or a minimum. But it could also be neither, depending on what happens with your first derivative or second. Your first derivative, is it changing from positive to negative, or negative to positive, or it could just flatten out and then keep going down, or flatten out, keep going up. Here's concavity and points of inflection. So if you're asked to find the points of inflection of a graph, you can say f has a point of inflection at some coordinate that you've determined, because that is when f double prime changes sign. If your second derivative changes sign, then it means your concavity is changing. If your concavity changes, that means you have a point of inflection. Okay. You can write f double prime changes sign, or this could be equivalent to saying f prime changes from increasing to decreasing, or decreasing to increasing. And it all goes back to this table right here. And I'll work many examples in upcoming videos, just so you can kind of see how we use these in free response problems. Related rates is a small topic, but in short, you'll always have a find, when, and a given and in your problem. So you'll have to find some rate. You'll have a moment in time, or a moment in the problem. It'll say the word when. And you also have some given information that you can fill in here. This is kind of the organizer that I use. And your steps to solving a related rates problem are, you have to set up your equation. Once you have it set up properly, you need to take the derivative. And it'll probably be d something dt. I'll work an example of that as well. Plug in your essential values, like what's given to you, plug those into the derivative, and then you solve for the missing rate that you were trying to find in the first place. And then the last box here is the mean value theorem. This is a very common topic, and I wouldn't be surprised if it showed up. But this has to do with finding a letter C, or x coordinate C. What you're trying to do in this problem is you're trying to figure out, when does the average rate of change in some interval equal the instantaneous rate of change. So at the top I'll put a rock equals I rock. So if you remember from the previous study guide, we talked about average rate of change being your slope formula, and I rock being your derivative. And so what the mean value theorem says that, so we have a theorem, so it's going to be if we have these things true, then something else is true. So the first thing that's true is that f of x is some function that is continuous and differentiable, meaning you can take the derivative at any point. In some interval from a to b, then you can say, so here's the then part, then there's a moment in between A and B where you can find the average rate of change is equal to the instantaneous rate of change. So I'll write f of b minus f of a over b minus a. So there's the a rock is equal to I rock, which is f prime of c. And then we can say where c is in between a and b. So I'll put a is less than c is less than b. So the essential guy right here is this one right here. And what most fear response problems try to have you do is figure out what is that value c. But I will work some examples in particular, and I'll post them under this section so that you can practice and see what a mean value theorem fear response problem is, and how you would approach that type of a problem.